Hello everyone. Today we are going to discuss about the plasma production in this class. Before that, uh, let's just recapitulate what we are studying in the previous class. So here, what we are showing you um, a plasma jet which is discharging in the upward direction, and this is the nozzle exit region, and this is the plasma plume which is discharging upward. And what is happening there inside this zone, and how the arc is getting distributed over the space within this plasma jet. So you can see here that I am showing this video when this plasma plume is coming out. So within this zone we have captured the phenomena that is happening inside this plasma plume using fast camera. And what you are seeing here, the plasma jet is having a central core which is coming out. So the current is basically going in the opposite direction as per the convention. So electrons are coming out like this, and they are following the this current path, and this is the current path. You see that now it is a perfectly U-shaped, and there is a cross connection over here. So the electromagnetic body forces which are being imposed, as I was discussing in the previous class, is because of the current loop that is being formed like this. So you see here, there is a current loop over here as well. So the longer path is like this, and this is the shorter path. You are seeing that the jet is going out. So you see that this is the basically the current path, and at the bottom region, the magnetic field that is produced by this current path, that is basically causing the instability to happen, and that is making an obstruction to the flow of the plasma. And you know that when the jet is structure is like this, perfectly U-shaped, then you are getting a perfect obstruction over here. Otherwise you are getting a slanty obstruction, and the kind of jet, a fang type jet, what you are seeing in the first camera photograph in previous lectures, that was because of that. So the kind of movement of this arc route, the current where it meets over the anode, through which it enters, so that is actually the arc route. And you can see that number of arc routes are possible, multiple arc routes are possible simultaneously. Like this one, you see this one and that one. So they were posing simultaneously, but they cannot continue for long. Only one will survive, and the other will just get extinguished. So temporarily multiple arc routes are possible, and they are always dynamic, as we are seeing over here, and they are basically pushing the electromagnetic body forces and causing the kind of instabilities what you are seeing in a plasma device. Now in this lecture, our motive is to understand the process of plasma production. So how this plasma is getting created, how we can initiate the formation of plasma in a device. We know that the Saha ionization equation tells you that what will be the equilibrium composition, but that is once the plasma is formed. But how to initiate the plasma? So that is the plasma ionization mechanism that I will be studying in this class. So the first thing that comes in this is the Townsend ionization mechanism. Now, how we are going to ionize a gas when the gas is initially neutral at room temperature. For example, suppose you are considering some argon or some nitrogen or some oxygen or air, all of them are not conducting at the room temperature because they are not having enough electrons to carry the electricity. Now, how to produce the ionization then? If something is neutral, they will not respond to the electric field. Then how will you produce the plasma? Now you know that at any temperature there will be certain electrons present in any gas. For example, in this room also certain ionized species, certain electron distribution you will be able to find, and they are originating from that ionizing radiation, or cosmic rays, or even the Maxwellian distribution is having a tail which are supposed to contain very high energy particles. So they are not very sufficient in number, but they are there and they can do certain ionization. So initially these stray electrons which are produced by this ionizing radiation or due to thermal properties of the gas that you are having there, these electrons may participate in the initial ionization process. Once they collide, once they are driven by the electric field, they will gain energy and they may collide and produce some more electrons. Those electrons will again participate in the acceleration process or gaining energy, and then finally what they will do, they will produce more and more electrons, and a time will come when you are able to produce infinite number of electrons in practical words. Actually nothing is infinite, so very large ionization you will be able to create, and that is the time when you say that breakdown has happened. So final goal of this study that we start today is to understand how we can cause breakdown in a gas. So for that we define the Townsend fast ionization coefficient alpha. So what is that? The number of electrons produced per unit length in the direction of the applied field in the process out of a single electron is the Townsend's fast ionization coefficient. So an electron is driven by an electric field, then it gains energy as it moves. Number of electrons that it produces per unit length in the direction of the applied field we will call the Townsend fast ionization coefficient. So what is Townsend's fast ionization coefficient? It is a number of electrons produced per unit length. Now we try to derive an expression for the Townsend fast ionization coefficient. Now the electrons are colliding. The mean p path depends on the number of molecules per unit length, number of atoms per unit length. If more numbers are there, definitely the free path will be reduced. So first we need to find an expression for free path x, possible free path x. If it gets an average free path of x, then the electric field E will produce a force on that will be E into E. This force into distance, the average distance x, that will give you the energy that has been produced. So if that energy that it gains is sufficient to cross the ionization potential of that atom, then it will be able to ionize it. So suppose we are having some free path x. So what is the probability of having the free path x? If there are n number of n0 number of say atoms are there, then the number of free paths that will be available n0 e to the power minus x by lambda 0, where lambda 0 is the mean free path. Okay. So out of an assembly of n0 electrons, nearly you will be having the free paths which is n0 exponential minus x by lambda 0 having a free path of x. Okay. So if that is the case, then let us assume that x equal to lambda I, that will give us the ionization potential. That is when E into E, that will be the force, and this x, that will be lambda I, then what will happen, that the total energy that it gains will be E into Vi. Vi is the ionization potential. So E and E both sides will cancel and you will get that lambda equal to Vi by E. So that is the your mean free free path for ionization mechanism to happen. So if the particles gain a free path of lambda I that equal to Vi by E, then it will be able to produce the ionization for those collisions. And what is the number of them? That is n equal to n0 exponential of minus lambda I by lambda 0. So that is as per the kinetic theory formulation. So we are now following the theory of kinetic theory approaches, and we are finding the number of ionizing collisions that will happen if there is an assembly of n0 number of electrons per unit length. So out of n0, this n numbers will be ionizing collisions, and so each of these collisions will produce one electron, and per unit length how many electrons are produced? So that is n, and that is nothing but the the Townsend's fast ionization coefficients. So we just replace n by alpha when we are putting x as lambda I, and then this alpha is equal to 1 by lambda 0 exponential of minus lambda I by lambda 0. And what is lambda I? This is Vi by E. Okay. So Vi is the ionization potential which is having a fixed value for different atoms. Okay. So if I want to know the fast ionization potentials of certain atom, so that quantity is fixed. Now N0 is fixed. How is N0 defined? It is defined by the pressure, and how it is connected with the mean free path. So it will be inversely proportional with the mean free path. Okay. So if mean free path we assume that it is lambda 0, then N0 is roughly very close to 1 by lambda 0. So we can just replace this N0 by 1 by lambda 0. So you remember that we are considering N0 per unit length. So that is how N0 equal to 1 by lambda 0, and then this exponential is there, and lambda is, as I told, it is Vi by E. So we just put this value over there, then we get the expression for this Townsend's fast ionization coefficient as this is 1 by lambda 0 exponential minus lambda I by lambda 0, and what we did actually, lambda I we have put as Vi by E, and Vi is a constant, so we have just now multiplied that to some constant, and we have presented that as a function of pressure as alpha equal to A some constant, then P pressure exponential minus Bp by E. So we are able to produce the we are able to represent the Townsend fast ionization coefficient in this form in terms of pressure and electric field E. Now when we are coming to the electric field, you know that electric field can be presented as the voltage applied divided by the distance. What is the voltage applied? It is the voltage between the two electrodes between which you are causing the discharge. And D is what? D is the distance between the two electrodes. So once we are having a specific discharge configuration, we can determine the electric field in terms of V and D. So we can write E equal to V by D. In that case, what will happen, that alpha will be expressed as a function of pressure, the applied voltage, and the discharge gap. And so that will be a very elegant expression, and we will be using this kind of relationship in the later derivations. Now what we are going to do, that total number of electrons that are produced in a gap of length d. Let us assume that some n number of electrons are impinging from the left side over an elementary length of dx. So this dx is actually the medium which we are going to ionize. This is the elementary length in that medium, and after it crosses the medium, then what we are getting? We are getting the number of electrons n plus dn. So this dn is the extra number of electrons that you have produced because of ionization in this elementary length of dx. So what we are getting, this dn is equal to alpha, the Townsend fast ionization coefficient, because what it says, it is the number of electrons per unit length per electron. How many number of electrons are impinging? N. So we multiply by n, and it is per unit length. So what is the length that we have considered is dx. So alpha n into dx will be same as the dn. So as per our definition, dn equal to alpha n into dx. So you just follow my arrow, then you will be able to understand the things what I am saying. So this is for a length of dx. Now, if we want to understand what is the total number of electrons that has been produced out of these n electrons, so that will be, you integrate this over n0 to nd. So n0 is the number of electrons that is been incident initially, and then nd is the number of electrons you are getting at the end of the gap. Then integral of dn by n equal to n0 to nd, that will give you the total number of electrons that has been produced at the end of the gap. So that is nd, and the integration is very simple, you know. So nd equal to n0 exponential alpha d. So this gives you the total number of electrons in a gap of length t that is produced out of n0 electrons, n0 incident electrons. So nd is equal to n0 exponential alpha d. So this is a very useful expression, and we will be using this expression in the later derivations. So apart from this, Townsend's fast ionization mechanism, what I have just discussed, there are ionization by positive ion collision as well. So electrons are colliding, and they were imparting the energy to the atoms, and they were causing them to ionize. So that was one part. That is the common thing, because electrons are highly mobile, they can pick energy from the electric field very quickly, and they can collide with the atoms, and they can ionize them. Although less, there is possibility that ionization by positive ion collisions also. So this is called beta mechanism of Townsend, likewise the alpha mechanism for electrons. So the number of electrons an ion produces by collision with gas atoms per unit length in the field direction, that we call as Townsend's second ionization coefficient. So this is ionization by positive ion collision. The second one is ionization by photons. You know the photoelectric effects. Photons produced by atoms excited through inelastic collision in the gas may be able to ionize other atoms as well and liberate electrons from the cathode if work function of the cathode is less than the photon energy. So this is some contribution from the cathode or from other gases because of the photons that is emitted by the excited atoms, and they may be excited by this inelastic collision in the gas. Now there are cathode processes, bombardment of the cathode by speeding ions is possible. So they emit secondary electrons and creating another source of electrons which can participate again in the Townsend fast ionization mechanism. So that way they will produce more electrons. So there are ionization by positive ion collision, there are ionization by photons, and there are cathode processes by which additional electrons can be created inside the plasma. Now there is some effect, if I don't tell that, so this ionization mechanism will be incomplete. There is something called panning effect. Sometimes a gas mixed with certain low percentage, you remember this is a low percentage of other gas, sometimes we call it impurity. So significant ionization at an applied potential much less than the ionization potential of the main gas. So it is quite surprising, and it was quite surprising for some time how a gas mixed with certain low percentage of other gas gets significantly ionized at a potential much less than the ionization potential of the main gas. The phenomena was first explained by painting, and the effect is known as painting effect. Now, he was a Dutch physicist and he worked during the Second World War, and like many inventions, this is one of them. Now, specialty is that there is an optimum percentage of the low concentration gas or impurity. Below and above that concentration level, the ionization is not that high. A metastable state of the atoms or molecules transfer its energy to another atom or molecule, causing the second one to ionize, even though the metastable particle itself doesn't directly ionize. Okay, so I'll just explain you with one specific example here, that neon. So neon ionization potential is 21.6 electron volt. This is quite high. This is natural because this helium, neon, argon, krypton, xenon, radon. So they are increasingly decreasing. The first one is having the highest ionization potential because of the that shorter diameter of the atom, and as you go to other atoms, they are having a bit lower ionization potential because they are now not that much influenced by the this nuclear potential. So anyway, so helium, then neon, then argon. So neon is naturally having more ionization potential compared to argon because neon comes first. It is having orbits which are closer to the nucleus. Argon is having longer radius, so they are having lower ionization potential. So neon is having the ionization potential of 21.6 electron volt, and argon is having ionization potential of 15.7 electron volt. Now, neon is having a metastable state around 16.6 electron volt. So this is the picture. Neon is having ionization potential of 21.6 electron volt. Argon, which will be used as impurity in this main gas, that is neon, and will not be exceeding 0.1%. We will just keep 0.1% of argon, which is having ionization potential much lower than that is 15.7 electron volt. And we note that neon is having a metastable state at 16.6 electron volt. Therefore, if the applied electric potential is increased gradually at 15.6 electron volt, no significant rise in current will be observed. Okay. So 15.6 electron volt, what is that? That is very close to the argon ionization potential. Now cross 15.6, nothing is happening. But as the potential reaches 16.6 electron volt, the current suddenly jumps to a very high, a very appreciable value. This happens because of the fact that when you are applying the potential equal to or more than 16.6 electron volt, neons are getting excited to the metastable level of 16.6 electron volt there. And this excited metastable state, when they de-excite, they emit radiation of energy more than the ionization potential of argon. So that is why argon concentration, although it is less, this is causing ionization in the argon atoms, and that is basically the reason for increase in the ionization that has been seen. So it is due to the metastable level of neon, but it is not due to ionization of the neon actually. But if argon concentration is increased or decreased from the value of 0.1%, the that current whatever you are observing, it will decrease. So there is an optimum concentration for which this painting effect is observed, and it is due to the metastable level that is present in the main gas. Now, some application of the painting effect we can find in gas discharges. So to enhance the ionization efficiency and lower the background voltage, the nuclear radiation counters to improve the detection sensitivity, and plasma light sources to help sustaining the discharges. Mass spectrometers and ion sources, we use this to assess the ion production. Now, you know that there is something we should like to discuss more in our next class. So, I'll just give you some hint on that. So, as a part of our this thing, this class only, I'll just continue that. Um, so, part of that I am just explaining over here, um, that DC breakdown criteria. So, you must have heard about the Paschen law. It gives you some relation about what should be the breakdown voltage for a gas at certain pressure under a given discharge configuration. Okay. So, the DC breakdown criteria or Paschen law is derived in this class. We will be starting with like this. There is a cathode, say K, there is an anode, say N, and N0 number of electrons are emitted from the cathode and they reach the anode. Okay. So, on the way it produces some or other ionization, and when they are colliding on their path to the other electrons, they are exciting them, they are allowing them to emit radiation, and that radiation is basically falling on the gas and causing that further electrons to get emitted via this the photoionization. So, you are getting one mechanism, the Townsend mechanism, by which the electrons are getting multiplied, and other mechanism, the photoionization, you are getting additional electrons produced. So, that is why I have shown this two. So, this is the Townsend mechanism, the pink one, this N is getting created, and on the way they are producing photons. So, this blue one, they are your photoelectrons. So, total number of electrons what are getting produced, N, is basically in Townsend mechanism, and that is added with the photoelectrons that has been produced as Np. So, N total is equal to N Townsend plus Np. Now, we define the this discharge configurations like this, that D is the discharge gap length, N0 is the initial number of electrons emitted by the cathode, Np is the number of photoelectrons that has been reaching the anode, N Townsend is the number of electrons generated through Townsend mechanism, and N the total number of electrons that has been generated. So, N Townsend, we know for a gap of length D, it will be N0 exponential of alpha D, where alpha is the Townsend's first ionization coefficient. So, we can write this one, this relationship N is equal to N Townsend plus Np, that is equal to N equal to N0 exponential alpha D plus Np. So, this is the total number of electrons that will be produced in this discharge configuration. Now, I will just tell this much only in this class, and in the next class I will explain in more detail about how to reach the breakdown condition starting with this configuration. So, we remember these definitions that we have produced, we remember what we are actually considering, the Townsend mechanism and the photoexcitation mechanism, and then we will proceed further. So, we will meet you in the next class. Thank you.